midterm exams have been graded. I got them back yesterday. I quickly went through it and then tabulated some scores, and will be returned to you at the end of today's class. So make sure that you get your exam back, and so make sure that you understand whatever the part you didn't get it from the actual exam. So compare that with the solutions or something. What we did yesterday, we introduced this uniform random variable which takes on this specific probability density function, some fixed number, but certainly depends on the location of this support of this random variable, alpha and beta. And then we went on to derive this CDF, which is a cumulative distribution function of this same x, uniform distribution that's between alpha and beta. So if the function value argument takes on something less than the left-hand point of this support, there's obviously no probability mass because nothing happened so far. So it takes on the value 0. But of course, the main concern is this middle part, which is a straight line with a positive slope of the CDF, PDF, which is 1 over beta minus beta minus alpha. And then the last one is just on top of those max value for this x, which is beta. Then everything will be included. So the cumulative distribution function takes on the value 1, and so on. So it's like 3 different parts, certainly not discrete, continuous. That defines this CDF function for this uniform between alpha and beta. Try a couple of examples, starting with the mean and variance of uniform between alpha and beta, and some numerical questions to ask you to compute certain probabilities involving this x, and then more realistic one, practical question like this one. And that was and then we introduced this normal random variable, normal distribution. In terms of its importance, this one is at the top of the list as far as the final exam is concerned. So PDF of this continuous random variable takes on this specific form, functional form, which involves this exponential function, coefficient of 1 over square root of twice pi, and 50 parameters. First, the standard deviation of this process, and mean of the process x. And that's how it defines PDF. The famous name better comes from the shape of this standard the normal distribution, because it's perfectly symmetrical around its mean value mu with a certain degree of spread, which is represented by this sigma. So given this PDF, we further went on to talk about its historical background and two key reasons why this normal distribution plays an important role in this course. First one, this one is used for the binomial approximation, which we'll get to do for the second half of today's class. And then more importantly, this is the key element in deriving or constructing the central limit theorem, which is a main topic for the remainder of this course. Then we stated that the mean and variance of this is a normal distribution with mu and sigma squared, it's just relatively, respectively mu, and then sigma squared. Actual derivation is quite complicated, so we skip that part. And we stated that these are the mean and variance of this distribution. Then we finish it with doing this transformation of this normal distribution. So given that original x is normal with certain mean and certain variance, easily come up with this linear transformation of this original x. You first multiply the x by some fixed number alpha, and then add up a different number. But then, interestingly, this result, which is a transformed xy, also normal distribution, but with a different mean. This is mu mean and mu variance, which obviously involves this two coefficient alpha and beta. So the way to divide it, we started with the CDF function of the new process, which is y, and then relate that back to original x. And then given the CDF of x, we first express the CDF x using this fx, and then we derive this PDF of this x, and related this PDF of y to the PDF of x, where the PDF of x is not because we do know that this x follows normal distribution. So that's how we show that this y is normal, but with a different mean of this and different variance of sigma squared times alpha times. standard normal distribution, as a result of this previous result, first subtract its mean and then divide the difference by its standard deviation. So one specific kind of linear transformation of this original x naturally follows another normal distribution, but mean happens to be 0. The standard deviation of variance happens to be 1, which is much simpler in standard case. So we call that as a standard normal, and then usual notation for this process is uppercase z. So whenever you see this notation, you automatically think of the standard normal process. So given this, we can move on and define this CDF function.
Transformation of this first subtract mu divided by sigma. So again, normal, this time mu of 0 and so on. So the PDF probably density function of this z is lowercase b x 1 over square root of twice by exponential to the power of x squared divided by 2. So the PDF usually we write it as x, but in the case of the standard normal, we typically use this Greek letter, which is called b. So we read it as b. So that's a lowercase. Then the CDF, cumulative distribution function of the same project this guy. Now the notation slightly changes. Not otherwise it's still p, but becomes uppercase. And then for this one you have to integrate it. Integrate it from negative infinity to up to x, because x is used as argument. You just plug this same PDF function down here as integral. This same CDF we are seeing. So first to divide its PDF, which is a specific case of a general PDF for normal with mu and sigma squared, and then use that PDF to divide its CDF function. Pay attention to that. There's a slight difference in terms of notation. First lowercase, and then this is uppercase. How do you compute this number? If x becomes one numerical value like a 0.5 or 0.7, you either stick with this definition, plug whatever the number you might have here, just put that as the upper limit of this integral, and then solve the entire equation out. That's one way. So of course that's harder than one way. Simple way, just to use a symmetry, and then go back to the table. What it is. It's just the same as this one, just work because you might find it a bit odd to have such a messy expression for that. So two salient features of this, the density of this standard normal is center is 0 because the mean is 0. It's a perfectly symmetric. The right half of that distribution will mirror image the other half, and then the distribution function is very smooth. So using the symmetry, we can easily compute the probability of the CDF function, whatever the argument of this function could be any real number. So the CDF, which is standard normal, let's see how the statement can be why the statement is. Takes on any real number. There's a peak in the middle. Here it is. So that's a field x, which is PDF slowly tapers off down to 0 eventually, but you have to be really so if you start at like a 4, and the other side should be -4, you pretty much cover like a 99.99% of all that distribution, but still the remaining 0.001 is not captured by this each extreme distance. So ruling those parts out, you're only concerned about this 99.99% between this -4 and 4. But what's this height of this center? How high is it? You see that this is the period. So simply plug 0 into this y. What do you get? Given the PDF for that, which is z in this case. So that's this curve. If you draw this one, you get this one. So what's the y coordinate for this value x? X equals 0. It's a coefficient. 1/square, which is approximately 2.9. Just under 4. And then it goes down either direction. So pick up any negative number, because there's a minus sign in front of this real number. Could have a negative 2. Sake of argument. And then the left-hand side, now uppercase P. Now look, this is lowercase. So that one is uppercase. Big upper capital P. Then if you plug this -2 in it, and basically what you're getting, area under this curve all the way up to that negative x. So this area, nothing more than this big P. Because the uppercase P is a CDF, if you integrate the PDF all the way up to -2, which is this value, that's nothing but the area under the curve, and that's the CDF. So either you solve this one out, plugging this -2 thing into this top one, and then merely solve the integral out, or you can do it the other way, using the symmetry. Think about the opposite of this one. So the opposite of this one, if you just keep the side itself, it's now positive 2. So the different way to computing the same area under this curve is basically first figure out the area under this curve all the way up to 2. So color that red. And you just move all the way up here and then start just at this. There is a red. Then if you subtract this red one from the area under the entire curve, which is going to be 1 because it's a valid PDF, that's basically what we're having. But because of the symmetry, area under this right tail should be exactly the same as that under this left one. So you need to retrieve the value of this CDF at the evaluated point negative x. Either way. You want to compute the phi at 2, you just simply plug this number into the CDF, or just compute that at under the -2, which is a negation of the initial value, and then subtract that from 1. So the answer is going to be the same. Purely because of this symmetry. So given this general normal distribution, you might have to compute certain number like x equals equal to certain number or less than that, which is nothing but the CDF value evaluated at specific point A. If you just go for this one without doing this standardization or
transforming into like a standard normal distribution, you just have to, how to compute this probability? If you ask you to compute this one, without doing this standardization technique, just literally compute this one, how do you do it? Well, X is just a normal distribution with U and sigma squared. You just use the definition. So the definition here, if X is a normal with minimum mu and variance of sigma squared, this probability there, X moving from all the way from negative infinity all the way, and PDF of this X, but then PDF is a normal PDF, so you have a whole expression. This computation is straightforward? Of course not. You give me 2 hours and I can do it. But you don't want to do it. So if you still want to compute this probability involving X, but then not, you don't want to deal with this messy expression, then what do you do? The trick is you always standardize it. So since X can be represented as this function of X, first subtract its mean, and then divide the difference by its standard deviation. 14 becomes what's called the standard normal, which is we did already twice. So the 14 becomes Z, but then the CDF under this Z function, Z process is known to us, which is this uppercase P, and then you instead plug in this fraction that appears on the y side of this inequality, and this is just a number. So in previous case, this little a could be like a 2 or 3. Assuming that the known value of mu and sigma or sigma squared, just first get this number, which is just a one fraction, and then you can go back to the distribution table of the standard normal and find out what's the corresponding probability. So any standard textbook on econometrics or statistics, either on the front or in the back, there's a tabulated number, which is nothing but the computed probabilities under different critical values. So your final exam will have that copy. So there's no way you can evaluate this in error, a different value for this A every time. So the way you do it, whenever you see the normal distribution, first standardize it into this Z thing. So subtract the mean first, and then divide the difference by sigma. That way you can make this entire X into Z. But the distribution for Z will be given by those tables. So use those tables, which will be provided to you during the exam. How do you read the table? You first have to get the table. So I get the copies, and then when we have to do it in class, I show how to do it, and then also do that during the review, so that you won't get lost during the final. But you use the table to compute this probability. Don't do this indirectly, just undo it. So another key reason why we have to introduce this standard normal distribution, because we want to compute probability like this one. When this probability statement involves this general X, which could be like a non-standard normal distribution with a known mean and a known variance, you can easily transform it into standard normal, and then refer to the provided table to pin down on this specific exact probability of that. Yeah, that's another reason. Practice. What about this one? So X is a normal distribution with a known mu of 3 and standard deviation of 9, or variance of 9. You have 3 statements. First, X is 3 bigger than 2 but less than 5. All X is bigger than 0. And the last case, which is the interesting one, you first subtract 3 and then take the absolute value, and then you have to make it strictly bigger than 6. These are 3 separate events, and then assuming the fact that X follows normal with this known mu and sigma squared,
you are asked to compute each probability. Let's do it now. Let's see what it comes. At least you should be able to do the first 4 views. The third one is a bit more complicated. So do it now, like 30 seconds, and see what you come up with. You can do the answers. At least you start with. So never ever forget, deal with the normal distribution, standardize it first. So if you standardize the x and then do the first one, you have to do something like this. So given that x is both the bigger than 2 but less than 5, you know that mean is 3 and then standard deviation is 3. First subtract the mean and then divide everything by this another 3, which is standard deviation, not the mean. And then the whole process turn into so-called standard normal, which is z. And having this each endpoint, negative third first, and then twice of that, but positive this time. First evaluate this CDF function at this 2/3, because you're dealing with now z. And then figure out this number, go back to the table of these tabulated numbers, and then do the same thing for this second end, which is negative third. If you figure out each number correctly, the computed final answer should be like 0.377. You just need to be careful about this first step. And the rest of them is just basically the same. Some of you might have done this back in high school. Remember that I did as a high school kid. I don't know whether they teach this from these days or not, because it was 20 years back. Have you used the distribution table for the standard normal before? No, so I have to tell you how before you use that. If you haven't, just let me know. I'll illustrate it at least once before you use it. But you get the copies. So if you get the final, which is typically like a 15 page long, it's a bit longer than the midterm, because there are more questions in it. Especially given this extremely good performance on the midterm, I have to make a final harder. Otherwise, it just gives you the same grades. The last 2 pages, photocopies of those distribution tables. So just to refer to those to compute numbers like this. So that's the answer to the first one. The other two, this. So second one is the same as before, so no difference at all. The only thing that you might want to pay attention to is just this the last important absolute value. So the same bracket x minus 3, and then take the absolute value of the difference, and that thing is bigger than 6 actually means 2 different things. X could be bigger than 9 or less than negative 3, but obviously those 2 events are disjoint. You cannot have them at the same time. So the probability of having both is actually the sum of each probability. And then for each, you standardize it, and then make it into z things, and then go back to the distribution table for the standard normal, figure out each probability, and then if everything is correct, you get the answer of 0.0456. so far? Not good, it was too easy. This one's a very interesting. Another example, the computation of certain procedure involving mobile distribution. Read a question like a 10 seconds and discuss what's happening. So magnify that. What's the expert witness? Anybody know what expert witness is? You know what an expert is, and you also know what a witness is. So what's an expert witness? Basically, it's an expert on some subject. The judge has to make a decision about a certain criminal case, but he's not an expert on all those different topics. So you have to borrow the expert opinions from somebody who knows the subject well. And those experts are, invited to the court to make some decisions about certain scientific facts. And those experts have nothing to do with the court, but outside the court, the juries will show to give some opinions. Those people with expert witnesses. So there's a paternity suit, lawsuit, brought up by this man, and he was traveling out of the country for a certain period of time. But then his wife got pregnant and gave birth to a baby. The problem is, here's the time. Baby was born at time 0, say. To make the expression convenient, say that this is 0. 290 days before, this guy left the country. And 240 days before this birth of baby, he came back. So during this time period, he was out of country. So there was a time that the baby was born, 240 days before he came back, and he left the country 290 days before. So for this time period, about 50 days, he wasn't in this country, he was traveling around. But then the baby was born here. Means what? So if this guy indeed the father of this born baby, either two extreme cases. The baby was, his wife got pregnant after he returned, which means the pregnancy is very short, less than 6 months. Or she had already baby before this guy left the country, which means extremely long pregnancy. Either is unlikely. Because the usual length of pregnancy is like 9 months plus or minus 10 days. So this is extremely unlikely, and this expert witness who's brought to this court by order of this, this judge, have to make some technical judgment about whether how likely this is. So how do you come to this probability? That this man indeed the father of this baby, given this circumstance. That's what the question is asking. So the mean value, if you just follow normal case, right in the middle actually. So the usual length of pregnancy is like 270, somewhere here. But in this case, it has to be either extremely long pregnancy or extremely short. What are the chances? Assuming that this length of pregnancy in days, assumed to be approximately normal, with a mean value of 9 months, plus or minus the standard deviation effect. Compare now. Let's see what you come up with. So you might want to start by first defining some proper random variable like the x. Define it to be like a certain event. And set it up involving that x with certain statement about it, like the less or bigger. And then obviously you want to relate that back to the standard normal distribution because you actually have to pin down on this specific probability.
So if you actually go ahead and compute this one, obviously these are two different disjoint events, extremely short frequency or extremely long one. So you have to handle them separately. So you can do it this way. First define this random variable x to be the length of the actual pregnancy in this case, which you assume to be the normal distribution approximately. And then you assume that this guy, the defendant who brought this thing to the court, indeed a father of a baby. But then what's the probability that happening? So in terms of x, that event basically says that x has to be either bigger than 290 or less than 240, and these two events are obviously disjoint. So you can break it into two parts, figure out each probability, and then add up. So the reason why you can add these two is because they are disjoint. And for each, either it's bigger than 290 or less than 240, it will be the same normal distribution. So the simple way to choose the probability. First, standardize it by subtracting the mean, which is 270, and then divide the difference by the standard deviation and figure out each probability based on those provided standard. Then if you do it, you'll see that the probability is not even 5%. 0.0241. For guy. Won the case, by the way. The judge ruled the case in favor of this man, and he was already sentencing. I don't know. It's the actual story. Anything so far? No. The either this type or previous one, at least one question involving this computing probability for normal distribution will be on the final. Last year there was one big part about something like this one, the same thing for the previous questions. In this one, we also include some questions like this. The main thing of today's lesson, normal approximation to binomial variable. So go back to binomial. Remember where it is. Something similar last month. This thing can be approximated by Poisson. But then the main difference between the kind of X approximation that we did last time and this approximation that we do now, both Poisson and binomial are discrete random variables. So there was no confusion. Either you compute based on this Poisson or just stick with this original binomial, it's just the same sort of computations. But now there's a big difference. This is continuous. So this one's discrete. Only takes the individual values, but this is a continuous. So over the entire real life. So the possible numbers taken by any variable like binomial is like a 1, 2, 3, 4, 5. But this one can be literally any real number. That's where the technical difficulty arises. If you have to approximate this one by this normal. But this approximation was quite well, as we will see from the following examples. So, first one, point tossing. So toss a fair coin, which means that the equal chances of success and fail. FF, you flip it 40 different times, which is a number of repetition in this case. And you call the head as success and tail as the failure. What you want to compute, the case that x takes on 20, which is only one occasion. Then first compute this one using the nature of this binomial distribution, and then approximate this one using this normal. And see how close they are to each other. So how do you first use the compute this probability using binomial only? Simple. So here's the x, which is number of times of that, followed by binomial. Try 40 times and success comes to the chances of that. Probability, which x takes on the specific value 20. Simply 40 choose 20. Success probability of half raised to the power of 20. The other half is probability of failure. Simple. But then how do you compute this one? The same probability that x takes from 20 using normal distribution. How do you do it? Using this. You just compute this one. If you compute this one, what do you get? So this computation is under this assumption. But if you have to compute the same probability over this one, you just strictly interpret this one as it is. What do you get? What's this probability when x follows normal? To 0, because it's a continuous random variable. Probability for any specific one point is always 0. So this is not the way. But then how do you do it? So x is a normal. In what case this is corresponds to the case of binomial 20? First 20 is there. If the x takes the value 20 under this normal approximation, certainly corresponds to the binomial x equals 20. But is that it? Certainly not. What about 20.1? So that's a certain possibility for this normal x. But if you have to translate this one in terms of this binomial x, what would that be? Still 20. Because you round this one up. And then that's basically the same thing as 20.2 with 20.4999. Something that you cannot round up to 21. And you can repeat it basically the same thing down this way. So the tricky part of this using normal approximation for this binomial, first write this thing in terms of binomial x, which is this. But then you have to translate everything in terms of continuous normal, which is this range. So any numbers within this range basically correspond to the case of x equals 20 under this binomial random variable. So you see that this is only approximate. So a lot of people miss this step, but they just somehow go wrong and then end up with incorrect answer. Please don't do it. So the first step, when it comes down to translating this binomial distribution to normal and continuous case, coming up with this certain range for this normal distribution, such that this range of these different values, real values, correspond to only one case under binomial, which is x equals 20. And pay attention to the fact that this second inequality doesn't include equality. It has to be strictly less than that. Because if you include this, the case of 20.5, if you round this one up, x is going to be actually 21, not 20. So you have to rule that one out. And that's the only part that you need to pay some attention to. Rest of it is the same as before. First, to standardize it, transform x into z, and express all the product or the event in terms of the standard normal, and then go to the distribution table for the standard normal. So the whole point, you just stay with this binomial case and then compute this probability in the original case, and you go to normal approximation, and here the difference between these two final answers is almost the same. And this cost even under the small sample of 40, not to mention when the number of repetition goes up to like 1 million. Almost the same. So you see that this n is rather small here, only 40. So even under this the small n case, the approximation works quite well. Not to mention a case like this 40 becomes like 1 million or 1 million. Almost the same. But then why do you do things this way? So the first, express it in terms of normal distribution and standardize it and then compute it this way is because when the number gets big, okay, if 40 gets replaced by some big numbers of 1,000, this computation is not quite easy. It's actually not very effective. Still you get the same as using this normal approximation, so why do you do it that way? College admission. So there's a small college out there. The ideal size for the first year incoming students is about 150. And this college, based on their own statistics from past years, knows that when they send out these admissions to various students, only about 30% actually accept and come. Because they also send out applications to various other schools. So if they accepted by both like the school A and B, if somehow he finds out that the second school is better than the first, although he was admitted by both places, he can only end up at one. So the other place actually lose one student. So based on their past history, about 30%. If they send out admissions to like 10 different schools, only about 3 out of 10 actually come to their school and become their students. So given their history, on particular year, they admit 450 students with a hope that more than 1/3 of them will actually come to them. And this question is asking, what is the probability? So this particular year, among those students who applied to this place, they accepted like 450 students. And their hope is that more than 1/3 of it, more than 150 students will actually come to the university and become the faculty of TS.
And what are the chances? And that's the question. And that one was actually put on the final last year. About half of the questions, they will have trauma or no. So how do you start this? Just wait for the question. Think about it, it's good practice. So how to set up the question and how do you connect this to binomial or normal distribution, and what way you can compute this, either the strict definition or some form of definition, maybe both ways to come up with a formula. As always, define some proper variable, random variable first, and then use some of the things that we learned today. Presumably, it's binomial approximation. So x could be what? How do you define random variable x in this case? What's x? So the main variable of our interest, x, should be anyone? Not interested? Will you be interested if I put something like this on the file? If you just blindly write down what's on the board, it doesn't help you at all. Because in the exam, you're on your own. So good way to practice it. So what should be x? So this year, among those applicants, they accepted 450. Their ultimate goal is to having more than 150 out of that 450 students. That sounds much more like a binomial distribution. Right? So binomial, for each one of those trials, there are certain chances of success. For other probably you would actually lose it, fail. But how many trials we have to do in this case? So when it comes down to binomial, you first have to figure out how many times you have to repeat the same kind of experiment, and what are the chances of success for each one of those trials. So how many times you repeat the experiment in this case? 450. So x should be what? So first define x. Number of applicants? It's not given. Could be like 500, 7,000, who knows? X should be number of some number. You said it's a binomial. So x follows binomial. Well, we have to define what x is. What's x? Well, if you don't know what x is, what's the success probability? So we're odd. We haven't even defined x, but then we proceed with the distribution. So you try 450 different times, but what's the success probability? 0.3, exactly. So what should the x be? Number of incoming students. So this is exactly the binomial case. You either, so what do you want to compute then? So compute what? So given this x and given its distribution, what do you want to compute? one. So since the normal is a continuous random variable, it doesn't have to be integer. But you want to keep x this under the binomial case strictly beyond the 150. So 150 is not included. Or even not 150.3 is not included because if you round that up, that one becomes 150 again. So it has to be strictly either equal to less than 50.5. And that one will become this 151, which is not allowed in this case. So they wanted more than 150, not 150. And then the usual standardization, so mean of n times p, n is a 450 and the success probability is going to be 30%. And do the same thing for the other end, which is just simply number. And then what's on the left will become the standard normal distribution because of this normal approximation for binomial. And the right end becomes 0.57, and that should be evaluated for this CDF function at this value. And the final answer will do everything correct. Not very high, not even 6%. So the probability of having more than a third of the admitted students will actually end up here. It's just over 5%, 5.59% to be exact. One similar question was involved in the new problem set. Number 5 of homework 4. So go ahead and do it and then see how it goes. Our solutions to the new one will be made available sometime next year. I don't want to review it now because you won't think. So first work on yourself. If you have any problem, refer to the post solutions. So date for the next quiz is 2 weeks from now, but if there's a request like from the previous class, I can delay 1 more week. Because I heard that the last week of May is the Universal Festival. So I don't want to be a party pooper. So in that case, but then the problem is there's at least 1 more quiz. But then the end of semester is like a June 14th or something, second week. So the last quiz must be either that week or before. Which means that the next quiz is going to be just a week after. So it's up to you. If you want to just do the quiz 1 week later and then have another quiz the following week, you can certainly do it that way. And what's even worse is the Monday is a holiday. The day before the quiz. Definitely does. What do you have here? 3 more distributions for this continuous random variable, then we are done. But then the remaining 3 is actually not treated at all. So the first one coming up is the exponential distribution, which has something to do with the geometric distribution that we did in the discrete case. Somewhat different, but in large part, those 2 things are related to each other. Just like the binomial is related to normal distribution, the next one coming up, exponential distribution, is related to the geometric distribution, the discrete. So that's the next one. And then we go over to the gamma distribution, and then the last one, which is the log normal, is the most important one. And then the remaining. But that one I'll do next week. So make sure they understand everything about this normal and standard normal and the relation between binomial and normal distribution. There is 13 of the plan. The 2 most important things for the final exam is what we will cover starting next week, which is a strong low large number, and above all, central median, which is the single most important topic in this course. And we will probably have to spend 5 lectures on that.